Welcome to this Giken online presentation. This presentation describes details and advantages of the press-in method. This presentation is divided into 6 main parts. Firstly, we will look at the silent piler, piling rig for the press-in method. Secondly, you will see the principles of the press-in method. Thirdly, applicable piles and penetration techniques will be shown. Next, we will introduce the Giken reaction-based system, also known as the GRB system. Next, we will show you the Giken implant structure. And finally, the presentation will conclude with some case studies. This shows the standard machine layout of the press-in operation. The operation comprises the silent piler, a hydraulic jacking machine, the power unit of the silent piler, and the service crane. As you can see, the silent piler is very small and compact for a pile driver. Next, you will see the mechanism of the press-in method. The basis of the press-in method is simple. The silent piler obtains its reaction force by gripping previously installed piles in the ground, which are called reaction piles. Then, based on the reaction piles, the silent piler installs piles into the ground using static loading. The silent piler begins from a reaction stand, which includes outriggers to be loaded with counterweights. The counterweights provide initial reaction weight to install the first 4 to 5 piles in the ground. After the initial piling is done, the counterweights and the reaction stand are no longer necessary, so they are removed, and the press-in work continues. The press-in method emits only minimum noise and imperceptible vibration. Therefore, it is completely environmentally friendly. This shows a comparison of the press-in method to the percussion method. And next is a comparison of the press-in method to the vibratory method. As the press-in method is essentially nuisance-free, it can be utilized adjacent to residential properties or train operations. Moving on, we will go over applicable pile profiles for the press-in method. The silent piler can install most of the prefabricated piles available on the global market. Firstly, U-sheet piles measure between 400 mm and 750 mm wide. Secondly, Z-sheet piles measure between 575 mm and 708 mm wide. Z-sheet piles can be installed by the silent piler either in single or double form. Thirdly, 900 mm wide hat sheet piles. Next, the king post combi wall, which is a combination of universal beams and sheet piles. Next, tubular piles measure between 600 mm and 2,500 mm in diameter. Next, tubular piles with interlocks measure between 600 mm and 2,000 mm in diameter. Next, the Combi-Gyro wall, which is a combination of tubular piles and various shaped sheet piles. Now, please take a look at this table. The vertical column on the left shows the silent piler models, and the horizontal rows at the top show pile profiles. From the left, U-sections measure between 400 mm and 750 mm wide. Next, the 900 mm wide hat section. Next, Z-sections measure between 575 mm and 708 mm wide for both singles and pairs. Next, tubular piles measure between 600 mm and 2500 mm in diameter. As you can see, Giken manufactures several silent piler models to accommodate a wide range of pile profiles, which can cover all levels of retained height required in today's construction industry. Next, you will see the penetration techniques for the press-in method. For sheet piles, there are 3 penetration techniques available for the press-in method. These are the standard mode for soft ground conditions, the press-in with water jetting mode for medium dense or stiff ground conditions, then the press-in with augering mode for hard ground conditions on the right side. For tubular piles, there are 4 penetration techniques available for the press-in method. Firstly, the standard mode for soft ground conditions. Next, the press-in with water jetting mode for medium dense or stiff ground conditions. Then, the press-in with augering mode and the rotary jack-in mode called the Gyropress method for hard ground conditions on the right side. Let's go over the techniques one by one, starting with the standard mode. Piles are installed with static load only. The silent piler self-moves during each pile installation, moving one pile forward. Secondly, the water jetting mode. With the water jetting mode, each pile has a special fixing holder welded on its toe to fix a water jet nozzle in its place. The water jet lubricates the pile's surface and temporarily and locally loosens and softens the ground. As the water pressure and water flow can be controlled depending on the ground conditions, ground disturbance can be minimized by this regulated water flow. After pile installation, the water jet nozzle is retrieved and used on the next pile. Thirdly, press-in with augering. The pile is mounted on the side of the auger and the auger simultaneously loosens the ground and the pile is installed. Thus this method enables pile installation to be carried out in difficult ground conditions, such as cobble or boulder mixed soil, underground obstructions or rocks. After the pile has been installed to the required depth, the auger is reversed and the disturbed soil is backfilled and reconsolidated. Next, the Gyropress method. The Gyropress system consists of the axial press-in system and rotary cutting function, which increases efficiency of the press-in system. The gyropiler installs tubular piles by pushing and rotating the pile into the ground. This system can penetrate through very hard ground and underground obstructions. Now please take a look at the installation sequence of the Combi-Gyro wall. In this example, sheet piles are installed first. After installing all the sheet piles, the chuck of the silent piler is replaced for the following tubular pile installation. In order to install tubular piles with greater spacing, the silent piler self-moves forward. After self-moving, the next pile is installed. Finally, tubular king pile foundation. Tubular piles measuring between 600 mm and 2500 mm can be installed by the gyro piler with greater spacing, typically 2.5D. Please observe the installation sequence. As shown, the piles with greater spacing can be installed by the gyro piler as long as reaction piles are fixed with the skip lock attachments, which have extra reaction bases. After installing each tubular pile, the skip lock attachment at the rear end is relocated to the front end to extend the reaction base. Also, the silent piler can extract piles by reverse sequence. If necessary, press-in piling operations can be carried out by utilizing only the top of the previously installed piles. This system is called the GRB system, also known as the Giken reaction base system. Please take a look at the installation sequence. The GRB system is our own construction system in which all the steps, including transportation, pitching and pressing in the piles, are completed on the piles. Each mechanical device stands on its own while gripping previously installed piles, so there's no risk of toppling over, and construction can be performed as long as there is space to fit the width of the machine. Hence, this footprint-free installation method enables substantial elimination of temporary work, therefore significantly reducing construction costs and time. We will go over applicable ground conditions for the press-in method. Firstly, U-sheet piles. Pile depth is shown on the vertical axis and SPT-N values on the horizontal axis. There are 3 penetration techniques for U-sheet piles. the standard mode for reasonably soft ground conditions with SPT-N value of around 20 or less, the water jetting mode for dense or stiff ground conditions with SPT-N value up to about 50, and the press-in with auguring mode for extremely hard ground conditions with SPT-N value over 50, and even cobbles, boulders, buried obstructions and rocks. Secondly, hatch sheet piles. As well as U-sheet piles, hatch sheet piles can be installed using the standard mode, water jetting mode and auguring mode. What we would like to highlight here is, as shown by the red and blue dashed lines, applicable ground conditions are different depending on the pile profile. Longer sheet piles can be installed in case of 25H, 45H and 50H due to its higher drivability compared to 10H. Z-sheet piles can also be installed using standard mode, water jetting mode and auguring mode, and are applicable from soft to hard ground conditions. As shown, applicable pile length can be greater in the case of double Z sheet piles compared to single Z sheet piles. Next, tubular piles. Since tubular piles have greater drivability than sheet piles, deeper penetration can be achieved, if necessary, more than 50 meters. For extremely hard ground conditions, there are two penetration methods available for tubular piles, the auguring mode and the Gyropress mode. As the press-in method can overcome difficult ground conditions, it is possible to install extremely long piles using this method. This slide shows a 59.5 meter long steel tubular pile being installed. Now, moving on to the Giken implant structure, which we propose instead of traditional gravity foundations. The implant structure is defined as embedded piled retaining walls and foundations installed by the press-in piling method. Now you will see a comparison between implant structures and traditional gravity foundations. Implant structures are much more robust than gravity foundations as they have high resistance against erosion and seepage. Also, being embedded into the ground, implant structures are resilient and maintain their serviceability even in extreme events such as natural disasters. However, implant structures require a minimal footprint, while gravity foundations require a large footprint. Now, this video shows a comparison between implant structures and gravity foundations using a reduced scale model Tsunami testing. This apparatus can simulate a maximum wave height of 6 meters and wave velocity between 10 to 15 meters per second. We put traditional gravity foundations on the right and implant structures on the left next to each other. The difference is obvious. The gravity foundations are easily swept away by the scaled Tsunami, while the implant structures well withstand and diminish the wave. Now we will compare the bending stiffness of the implant structure to cast in situ board pile walls. Firstly, sheet pile walls versus RC walls. This graph shows the wall bending stiffness EI in kilonewton meters squared meters on the vertical axis and the wall thickness in millimeters on the horizontal axis. As the graph shows, sheet pile walls have similar bending stiffness to those of RC walls up to 900 millimeters in diameter, although the wall thickness is approximately only 2/3 of RC walls. The next graph shows cost comparisons of sheet pile walls and cast in situ board pile walls. The vertical axis shows cost including both material and installation. The horizontal axis shows wall bending stiffness. As the graph clearly shows, sheet pile walls are much more economical compared to contiguous walls and secant pile walls based on the same wall bending stiffness. As shown, up to a 40% cost reduction is achievable with sheet pile walls. Next, we compare heavy-duty implant walls versus RC walls. Wall sections are shown on the right. The degree of bending stiffness increases from the bottom wall section. From the bottom, secant pile wall shown in yellow, contiguous wall in green, Combi-Gyro wall in red, Combi-Gyro wall composited with concrete in the dotted red line, tubular pile wall in blue, diaphragm wall in black, and finally tubular pile wall composited with concrete in the dotted blue line. As the graph shows, Giken implant walls have similar, if not greater, bending stiffness compared to high modulus in situ concrete walls. Therefore, if the conditions are suitable, implant walls can be effectively used in place of in situ concrete walls. As shown, the heavy-duty implant walls in red and blue have a generally similar cost performance to in situ concrete walls. Now we will highlight some actual examples of major implant structures. Firstly, cantilevered major retaining structures. This project is a road widening project from 2 lanes to 4 lanes. Due to the presence of a steep hill along the existing road and a neighbouring residential area, a 13-metre freestanding retained height was required to widen the road. In order to satisfy the design requirements, 2,000mm diameter tubular piles were installed. The photo on the left shows before construction, and the right side photo shows piling works in progress. The design deflection of the retaining wall was 50mm. After excavation to the required depth of 13 metres, the deflection at the top of the retaining wall was only 25mm. The implant structures are durable and long-lasting structural components. Therefore, they are often used as permanent structures with a long design life. In this project, tubular piles were installed as a permanent road retaining wall with a design life of 120 years. Next, deep cofferdam. Tubular pile walls can provide excellent water tightness. Together with their great bending stiffness, they can be utilized for a major water enclosure. This example shows a tubular pile cofferdam directly installed in a canal with water retention of 10 metres. It has enabled the construction of a train station box in the canal at Canary Wharf in London. As water tightness is required on the interlocked tubular pile wall, each interlock was grouted with geotextile. In general, the permeability of grouted interlocks ranges from 1.0 times 10 to the power of -6 to approximately -8 centimeters per second. So excellent water tightness is achievable with this system. This is the completed train station. The next case study involves a sheet piling for load-bearing permanent basement walls. In this project, the specified working load was 1,100 kN on tubular piles and 500 kN on sheet piles. This is a 7-storey commercial building supported by the basement walls. Initially, the piling was used as a retaining wall in a temporary condition. Then it was connected with the basement slab and ground floor slab with shear connectors as a permanent basement wall. This slide shows the slab connection details. First, shear studs were welded onto the pile surface as slab connections. Then, in order to provide water tightness, water bar plates were also welded onto the pile surface. This slide shows the actual slab connection. The next slide shows the waterproofing details. In order to prevent water seepage through the sheet pile wall, each interlock is normally welded. For waterproofing of the slab connection, hydrophilic strips, which are water-swelling materials, are normally applied to the sheet pile surface and water bar plates, as shown on the slide. Then, the basement concrete is cast over the slab connections. This is the completed basement wall with a surface coating. This is the tubular pile area at the entrance approach. Because implant structures are embedded, they are extremely resilient. As such, they are often used for coastal protection works, as shown on the slide. This is the completed coastal protection. This is a photo of the same structure from a different angle. Implant structures are also used for the rapid construction of tsunami or tidal barriers using precast concrete segments. Now we will illustrate the versatility of the press-in method under difficult working conditions. First, piling works above water. As the silent piler is able to utilize the top of the reaction piles, a temporary platform is not essential. These are examples of port and harbour improvement works. This is another example of Cofferdam installation above water. Also, the press-in method does not require a temporary platform when working at height. In this example, the piles are projecting 10 metres from the ground. This shows the front view of the piling works in progress and the completion of the project. As the silent piler is very compact, it is capable of installing piles within a low headroom. The press-in method in this working condition is called the overhead clearance method. Next, you will see machine layout diagrams. This shows the cross-section. This shows the side view of the machine layout. With the press-in method, the length of each pile segment can be maximized. Also, this slide shows that railway operations are not interrupted. Therefore, piling works can be carried out during normal train schedules. Here you can see the post-installation and completion of a bridge pier reinforcement. Now, piling works carried out on inclinations. As the press-in method is a footprint-free installation method, it can be carried out on inclinations as well. The silent piler can perform even on difficult degrees of inclination without impacting the surrounding environment, such as train operations and residential areas. Further highlighting that the press-in method does not disrupt operations, this process can be carried out during the day. Sometimes underground obstructions are a major problem for piling works. This project is an underground station box construction. During installation of the retaining wall, some sheet piles encountered large boulders as shown on the slide. However, the press-in with Augering method enabled the pile installation to be completed by cutting through the boulders. This shows actual sea-wall upgrading work. Behind the eroded seawall, there is road and rail traffic. As it was effectively unfeasible to suspend traffic, the Gyropress method was used. Due to the space limitation, tubular piles had to be installed by cutting through the existing concrete seawall. This is another example of river revetment wall upgrading work. With this method, removing or demolishing existing structures in advance is no longer necessary. As a result, construction costs and time can be minimized simultaneously. That completes this Giken presentation. Thank you for watching. Please feel free to visit our website for further information or send us an email if you have any questions.